It is quite a joy to get a chance of discussing moulds and multizetas in front of an audience of conoscenti. So all thanks to the organizers for making this meeting possible. I propose to do three things. First, recall the basic essentials about the Flexion structure, ARI-GARI, and how multizeta algebra fits into the picture. Then, in the second part, discuss essentially the uncolored multizetas and the machinery for their reduction into irreducibles. That part will be kept at a survey level because this is not exactly new and the subject is vast. So I want to devote at least half an hour to the third part, which is quite new and deals with colored multizetas, especially two-colored multizetas, and calls for, again, algebraic methods, but quite distinct from the other, from the ones that apply to uncolored multizetas. So let us get started. Fine. So our basic tools will be so-called B-moulds. They are moulds with a two-tier indexation, U's on upstairs and V's downstairs. But it's more than just a double indexation. The thing is that the U's and the V's interact in a very specific way. The U's get added cluster-wise, and the V's get subtracted pairwise, and always in such a way as to preserve these contractions. So everything, all the operations we are going to use can be built from four very basic and simple operations, the four elementary flexions. They are relative to, always relative to a splitting, factorization of the sequence of W's, of the double sequence under consideration. So take one such sequence, and the four flexions go by pair, then they go by pairs, and look at this. You see that the two upper indices get added to the corner index here, and downstairs it is exactly the reverse. The corner index gets subtracted to each of the preceding indices. Well, and for the second pair, it is exactly the reverse. So throughout, we are going to use the shorthand. U index, sub 1, 2, 3 will denote U1 plus U2 plus U3, and for differences, we are going to compactify everything, the notations. V sub I double dot J will stand for VI minus VJ. Okay, so here the whole Flexion landscape is dominated by a basic involution, which you will see in a moment what it means in terms of multizetas, but here is the definition. It exchanges the U's and the V's. Again, it turned the U's into sums, partial sums, and the V's into differences, and again, in such a way as to preserve the contraction. And, well, it is an involution. And the interesting B-moulds are typically, they typically possess a double symmetry. The B-mould itself has a certain symmetry type, And the swap P, the effect on it of the swap evolution, has again another symmetry. It may be the same, it may be something else. So this is now something more interesting. The algebra and the group structure on it. Loosely speaking, you might say that this Flexion structure is the sum total of all interesting operations that can be defined, constructed from these four basic flexions. But you will agree that as definitions go, this is not this is slightly wanting in precision. So let us be a bit more specific. Statement up to isomorphism, there exist exactly 7 substructures, pairs of group, Lie algebras in group, the group that goes with it, which can be constructed from starting from the flexions. But only 2 of them, 2 of these 7, have the added distinction of preserving double symmetries, of being interesting for our purposes. And moreover, when applied, they are different. But when restricted to B-molds that have a double symmetry, they do coincide. So there's no agony of choice. We simply pick the simpler of the 2. This is the ARI-GARI pair. ARI is the algebra and GARI is the group. Here is the definition. You first introduce operators which are actually derivations. Derivation with respect to the multiplicative structure of the B-mold algebra, because on top of the flexion of the inflected operation, of course, they can be subjected to ordinary mould multiplication and the bracket that goes with it. So with respect to the ordinary uninflected operations, they are derivations. And, with the arit is a derivation. And the next line defines a bracket, when it is a Lie bracket, in terms of these derivations. And when you go back to the operator, you find that this is actually, it actually defines an action, or rather an anti-action of this algebra on the B-molds. There's no circularity involved in the definition. And the definition for the group is slightly more complicated. We first defined garit of B is an isomorphism with respect to group multiplication. And again, on the second line, you see how from that isomorphism you can define mu is ordinary mould multiplication. There are so many operations that we cannot devise symbols for each of them. So we have to resort to short combinations of letters. So as you see, the definition in the GARI product is highly nonlinear in the second argument. Because there are many B's on the left-hand side, and because these ones, the last ones, are themselves multilinear in B. They are the inverse of B with respect to mould multiplication. So this is and the main thing is that, of course, we'll see that in a moment, these two, this algebra and this group do respect double symmetries. We'll see which ones in a moment. So something about the origin, because this is an artificial sounding definition, and it's only decent actually to explain how we came to this. So there is one origin in analysis. This is something, this algebraic structure which arise from analysis of a virtue of special importance about them. They are natural. They are almost guaranteed to be natural and important. In this case, without going into details, the thing is, when you study singular perturbation, well, think of a nonlinear differential equation, ordinary differential equation with a small parameter epsilon in front of the leading derivative, and expand everything in terms of that, in terms of epsilon. You cannot expect conversions, of course, And, but you get most of the time, under very mild assumptions, conversions plus resurgence plus resumability. But the thing is, when you try to figure out the nature of the singular point in the Borel plane, you get something very complicated, and the singularity omegas in the Borel plane they are made from two ingredients. Things like the U's, which have a certain rigidity about them. They depend only on the leading terms of the differential equation, and then V variables, which can be anything and which depend on the singularities in the multiplicative plane. And the two things combine in a very specific way, which is dominated by precisely the Flexion combinatorics and even the ARI-GARI product factor. The ARI-GARI operations emerge naturally from that context. But there is another origin, purely in mould algebra. In mould algebra, without any flexions and with only one sequence of indices, let them be used. There are two basic operations, multiplication and, of course, composition. And if you combine them in a suitable way, you can recover the ARI-GARI structure, at least for the U's. But the thing is, once you know the flexion operations for the U's or for the V's, you can automatically, in a unique way, actually complete it for the W's, for the double indexation. So this is, and there is more than that, actually. If you specialize the ARI-GARI structure to certain subalgebra, very large, so to certain ideals, then you recover the uninflected structure. So you go from that. This is a shuttle, actually. So the two things are very closely interlinked, intertwined, and well, all this is to say that the appearances to the contrary, the flexion structure is something extremely natural, and with a claim to existence or a claim to attention that can be buttressed in any numbers of ways. So enough of heuristics. So well, this is just to recall the two basic encodings of the multizeta. You're all familiar with that. The first encoding is given by polylogarithmic integrals, and the second one by harmonic sums. Upstairs, in the WA, the indices are unit roots or zeros, and in the harmonic sums you have the weights, SIs, and upstairs they are the unit roots, but in logarithmic notation. A unit root is written as epsilon e to the 2 pi I times an epsilon, which leaves in Q quotient by, in Q modulo 1. Fine. And then there are the familiar conversion rule. We can go from the one to the other and back. And the convergence assumptions, and then the three parameters that will dominate everything: the weight, the length or depth of a multizeta, and then the difference, which is the degree. It will be the degree in our set. The degree of a polynomial, actually. So the algebraic constraint, all of you are familiar with that. The first, each encoding comes with its own multiplication rule. The first encoding, the mould is symmetral. The second one is symmetrel. That is to say, when you multiply to such multizetas, you have to add contractions, additions of the which apply to both indices, including the colors, and then two additional rules. The conversion rule and the rule of color consistency. If you average on a certain number of colors, you have to get something, and they are And the main meat actually is in the two symmetries. They are just additions. Let us not waste time on that. And so the thing is to not only to compactify the things, but also to work efficiently with these multizetas. We have to go to generating series that will turn out to be generating functions and meromorphic at that. So from the symmetral encoding, we go to generating function ZAG, G for generating, and which is defined in this special way, which is called amplification, and which automatically turns something symmetral into something, it adds a new level of indexation, but it turns a symmetral mould. It keeps symmetral, and it keeps alternal. And then the definition for the second encoding is even simpler, and then it changes, it modifies actually the second symmetry. It was alternel, it was symmetrel, and it becomes something else. We'll see which symmetry, what change it undergoes in a moment. For the moment, let us mention that these two generating a series of functions, they are actually meromorphic functions, and with a very remarkable structure. They have simple poles, I mean multiple poles in the sense that there are many variables, but if you, with respect to a given variable, there are no multiplicity, there are simple poles. If you freeze all the variables save one, then you will get something multiple. And they have even a compact expression with a dominant part, you see here, which is it has got a simple expression and just a simple correction, which is consisting of scalar terms. So, and that will be, now next. So let us rewrite, let us see how the constraint, the algebraic constraints which you're going to exploit, what changes they undergo under this change from scalars to generating functions. The first symmetry, it doesn't change. It's the second symmetry. You see, instead of, in place of the elementary contractions, additions, you get these differences. You divide here by a difference of v, but in such a way that if that the poles get cancel out, if you have something polynomial, it stays polynomial in the end. So the conversion rule also undergoes a change, which actually is even simpler than with the scalar multizeta. Then the constraints of color consistency also can be written in a very compact way. They involve, you see the blue terms are just corrections. They are moulds which belong to the center of GARI. The center of GARI is exactly that. It consists of very special terms. They have to depend only on they vanish when the V's are non-zero, and when they are colors, in this case, and they depend only, and even when the Z's are zero, they depend only on the length of the sequence. So they depend in the end, in the last analysis, they depend only on a sequence of numbers. And one central mould is responsible for the conversion rule, and another one is responsible for the color consistency. So but let us not fuss about this. This is so why is it so important and so useful actually to turn to this? It's not just a question to turn to generating functions. It's not just a question of simplifying and compactifying everything. There is more than that. Actually, in this framework, you can introduce poles at the origin, things which, objects which will prove absolutely essential in the sequel, but which cannot be defined or even made sense of in any of the competing frameworks. And then they are meromorphic functions, these Zig and Zag. And when you look at the way the relations, the algebraic relations between multizetas are derived, they all derive from ways of rewriting multiple poles. And so they find themselves at the outset in deep agreement with the nature of the algebra that commands the relations between multizetas. Okay, so let us...
N1, 2 is N1 plus N2, I suppose.
Yeah. This is the shorthand which we use throughout. So, this was... So let us very quickly, because I want to save time for the new things, let us very quickly list some of the results that were obtained from in this way. Well, the Euler considered multizetas of length 2, but they are very special and they are not typical. Actually, I mean, the reduction into irreducibles is absolutely elementary. The real multizetas appeared in the late 70s, but they are special multizetas. They came up during the investigation of the invariance of geometric object, in this case, identity tangent local diffeomorphism. This is not at all to stake a claim of interiority. I'm well aware that David Broadhurst also encountered multizetas very early on, and for all we know, other people may have seen. But the point here is that these are very special beasts, actually. If you regard them as a subject only to those relations, those algebraic relations, which are responsible for making the invariance invariant, then you get a system of relations which is slightly weaker than the two quadratic relations. They are, let us say, 1.5, but they are enough. Actually, they lead to a very interesting result. You can eliminate all multizetas of degree, the degree being the weight minus the length. You can eliminate in an algorithmic way, a very efficient way for doing that. And that's another result. Well, palindromy formula in the Ihara framework, there are two ways of writing an element, and the people noticed that they are invariant under this involution, and this was proved in this way with this machinery, and then the eliminations of all partial weights of index 1. In the case of uncolored multizetas, there is an even more precise statement due to Francis Brown. But the thing is that it applies to all multizetas, and the underlying combinatorics is very beautiful, and there is a nice functional projector on this on the space of unit-free multizetas. Okay, this is just to now let us come to the main point, to this, to what is arguably the central piece of the Flexion landscape. This is a special mould, the polar mould PAL, and the swappy is PIL, which is made from poles. P, capital P, is simply 1 over capital P of T is throughout 1 over T, and capital Q is up there, I mean, trigonometric function, 1 over cotangent. And they are characterized by these properties. They are homogeneous polynomials in P of ui's, and the partial sums starting from 1. And the same for the trigonometric series plus P to the squared. And now These two B-moulds, especially the first one, PAL, PIL, they can be defined or characterized in any number of ways. Not any number, but many ways. They have no end of interesting properties. They are absolutely key to the understanding of the reduction of multizeta into irreducibles. They will intervene at three absolutely crucial junctures in the next steps. And main thing, they cannot be defined. They cannot even be understood in any of the alternative frameworks. And they have this double symmetry. They are as/as, meaning symmetral, with a swappy that is also symmetral, but without a certain technical condition bearing on the first component, which means that the set to which they belong is not exactly a group, it's larger than that. We'll see that in a moment. Anyway, so this is the two examples of important and very helpful B-moulds. So the first intervention of our B-mould is with them we shall construct an operators that have the merit of exchanging double symmetries. We are interested in the symmetries symmetral slash symmetrel and alternal slash alternil, but they've if you recall the definitions, alternil and symmetrel, they mix up various lengths, so they are slightly inconvenient. Whereas the other double symmetry, alternal slash alternal and symmetral slash symmetral, they involve only sequences of the iso length, so to speak. They do not compel you to envisage different lengths at the same time. So they are much more convenient. So we have to shuttle from one to the other, and eventually, of course, revert to the as-is and al-il double symmetries. But the operators for doing that are precisely made from the PAL operator through its conjugate action. So, and then second intervention, we, in the process of constructing a basis in our algebra of the moulds with a double symmetry, we'll have to correct, there will be singularities will be produced in the induction, which have to be removed. But they have to be removed. It sounds simple, but it is not, because we have to respect the symmetries in the process. And we have to produce, we must be able to reproduce, for the sake of compensation, any given singularity of a given type and double symmetry. There is a machinery for doing that, and that, once again, it relies on the mould, on the magical mould, PAL-PIL. So there are three things. The operators themselves, the singulator, the produced singularities of a specific type. The singulate, the end result, the singularity you want to produce, so as to eliminate it and compensate it. And then the singuland, which is the regular mould to which you apply the operator. And well, we cannot sort out the definition, but the main element again is, the main ingredient by far is this, again, once again, this mould PAL-PIL. And so the whole procedure for constructing moulds, which possess these three qualities which do not agree well together. This double symmetry and this quality of being an entire function, they do not agree well. You have to be very extra careful, actually, to preserve everything. So, suppose you manage to construct such a B-mould in the algebra. So you're starting from alternal slash alternil. You go to the alternal via the exchanger, and then you make, depending on the parity of R, you add either 0, which is B alternal enough, or you a singulate produced in precisely the way I mentioned to compensate it, and then you end up with something which is you get your asking, you get to the next step. Of course, I mean I have to rush through this, but this is I mentioned, at least I pointed I explained what makes the process work. So the thing is, you have to select in this induction, you have to select your singulates, the polynomial moulds, very carefully, and that means that you have to verify certain equations, algebraic equations of a very specific type. The de-singularization equation, the one up there, but with the colors. But this is the first, the most elementary composite singulate, a singuland. And but here again, without the colors, in the case of Uncolored, and in a standard notation to make it more, in a more familiar sounding, plus earlier terms. In this case, in terms of one variable. So, and the general de-singularization equation, it is has a very specific form. I mean, it involves coefficients which are either 0 or plus or minus 1, and then it involves a sequence of u's transformed by elements of the special group. This is quite a quite remarkable system of equations which enjoy many closure properties. And in the end, when the program is actually will end, one can decompose, one can factor the generating function into 3 basic factors. The factor 1 will carry essentially the powers of p squared. The second factor is going to carry even, let us say, even irreducibles, or even, and the third one, odd irreducibles. And the thing is, the last factor separates from the first two very easily, but you have to work much harder actually to separate the first one from the second one. This will be, this is what we are going to end in the end, and the ingredients up there, I mean the rows, the scalars, they will be the reducibles. And from this formula, everything will follow. But to make it work, we need actually a basis of these in the algebra of, with alt/il, and this there are 2 obstacles in the way. There are many difficulties, but let us concentrate on the essential difficulties, not on the trivial ones. There are 2, and they are even closely linked. The first one, let us call it infinitude. You have the first symmetry involves a relation between a sequence W and its transform under essentially the symmetry group. And the second symmetry does exactly the same, but with respect to the not W, but the swap and each of them is finite, of course, but the 2 together, when you combine them in one system of coordinates in the original W's, they generate an infinite group, except for r equal 2. This is precisely the reason why length 2 multizetas are so elementary and uninteresting. And so this, in particular, this precludes the existence of functional projectors on the space of double symmetries. You have to construct them. You cannot simply project onto them. And the second difficulty, think of the scalar multizetas. if you are interested in the multizetas of a certain weight, S, equal to that weight or less than that weight, there are obstacles to using the filtration by the length or by the degree. And they are quite different in the case of uncoloreds and in the case of colors. Absolutely, yeah. And in the case of uncoloreds, once you have, there is no problem constructing the induction works fine. I mean, at each length you express everything, and you can proceed nicely. But once you have got that, there are relations which there are indeterminacies which will get corrected at a given length. There will be, when you express an element of the algebra in terms of a basis, there will be indeterminacies which will get cancelled or made good only at the later stages. In the case of B-colors, it is exactly the reverse. Once you have given a basis, there are no ambiguities in expressing an element of the algebra. But the thing is, when you express length after length, the constraints, the two double symmetries, you seem to get you get more degrees of liberty, which will be cancelled later on. So they are the same. In the end result is the same: difficulty, an imbrication of all moulds, but the precise mechanism is exactly the reverse. So in the case of uncoloreds, there is one, I cannot mean, there are mountains of structure and cartloads of formulas, but I concentrate on the essential state. The thing that makes everything work is to enforce rigidity, and instead of working with polynomials, which verify elementary B-molds of that form, which are not free, do not freely generate. They do not generate all B alternals, and they are not free. But if you go to polar functions with simple poles, if you start from these, then both difficulties vanish. They are free, and they freely generate a certain algebra of multipolar functions, which is exactly the algebra which you need, which you require. Actually, the exponential of the elements of that algebra will be the function tag and zig. So, without entering into details, this is the one step that saves the day, makes everything work. Enforcing rigidity by going from polynomials to polar functions. And there's the de-singularization. When you do that, you instead of having as unknowns the singulans, you have you take as unknown their multi-residues, you see? And the multi-residues verify the same type of equations, but then instead of having something underdetermined with many solutions, you have something which is well determined and seems overdetermined, but actually has a unique solutions. And in a word, it works. I mean, this is a very beautiful subject, but it has been written down, and I'll write something even more precise. And you can, at the end of the day, what you get is in the two encodings, zig and zag, you have your scalars, the rows, and if you want, they have themselves a nice expression, which is, as I said, exactly midways between the two encodings, which is nice because neither should be privileged. Actually, they are on the same footing, and they are exactly midways. And the scalars, the thetas with sequences are nice rational numbers with very beautiful properties, but I cannot go into that. It's a world unto itself. But anyway, rigidity is the magic word. So that against I think I got across. And when you have that, you can express any multizetas in terms of the irreducibles. You take the second line, you take a Taylor coefficient, it is a multizetas, and you expand the function, and you see what you get in front of the coefficient, and it will be your multizeta expressed in terms of irreducibles. Of course, I mean, now, there's another way of doing that. I cannot go into that, just mention one point. Instead of enforcing rigidity by going to polars, to meromorphic functions with simple poles, you can enforce rigidity by, you stay with polynomials, but you add additional constraints. I cannot explain which ones, but in the case of the first singulands, here they are written. You take them in a subspace of the polynomials of a given degree, and something magical happens, which is not until you have the rigidity, you have unicity of the uniqueness of the solution, but on top of that you have a very astonishing property. These polynomials have coefficients which have a nice expression in terms of prime numbers. You see, it is a fact of, I'll just say it in words, it is a fact of life, of mathematical life, that you cannot produce non-tautological formula that produce prime numbers. You have to inject them in, this is a sleight of hand, actually it's uninteresting, but in this case, you have something that comes very close to doing just that. Well, I explained it in the slides. By the way, I posted these slides on my homepage, and I'll beef them up slightly on my return, so there will be explanation, and these things which I have to skip will be perhaps easier to understand. So we pointed out to the main difficulty, these double curves of infinitude and imbrication. In the case of Uncoloreds, we saw a way, rigidity, to overcome this, these double curves. And in the case of the coloreds, and also the multicoloreds, well, I'll discuss only the bicoloreds, there is a new, absolutely different technique, but which salvation comes from a new technique, which also brings in its wake a lot of very interesting structure. So it's doubtful whether I can explain it in detail, but at least I can explain the overall scheme. There are 3 steps. You see, take a large weight and take colors, 2 colors, 1 and 1/2. 2 colors. So for a large S, there's a huge number of data, of course, due to the colors, which multiply everything by 2 to the S. And so the first thing is to reduce this chaos of data. And you do that, surprisingly, by suppressing all the V dependency. You take all in the level of the scalars, you take all partial weights equal to 1. That is to say, in the case of the generating function, you take all the u's equal to 0. This is a dramatic reduction, and you should expect a huge loss of information, but actually there is none. Everything, yet there is no loss of information. We shall explain why. And then you do something very strange. You change, so you've lost the degrees, the U dependency, but you have retained the colors. You have less objects, but still quite a lot, and you have no gradation. So that you are not. This is not satisfactory, but you will turn the colors, the lower indices, into upper indices. Through the trick of amplification, we'll see it in a moment, and we'll get 2 objects, which have this time the satellites, and they have no colors, but they have a polynomial, they depend polynomially in the upper indices. And then we can recover everything algorithmically, And in the case of the Uncolored, you can recover this through very simple and absolutely surprising formula, because you have, you see, you've done very unholy things. You've suppressed the degrees, you have changed the colors, and you have done things which ought not to work, but they do work. And there's, you get two satellites in the end. You will be working with two satellites, which are simple, and they will restore the gradation in length. You will be able to go from 1, 2, 3, etc., without bothering about what comes next. And the ARI-GARI structure is going to be redefined. It will redefine itself, not without you doing anything. It will get redefined on these pairs, or in the case of many colors, on the tuples, in a very interesting way. I mean, it induces a structure which is comes as quite interesting. Now, there are still 12 minutes, I think, to go. Let us at least explain how the main three steps work. I mean, so first, we go to the extremal algebra. We suppress all partial weights other than 1. That is to say, we take all u's equal to 0. Now, this should entail a huge loss of information, but it doesn't, in fact, due to two lemmas. The first one is highly non-trivial, but extremely helpful. When you have a simple symmetry, alternal, and that means it implies a certain identities with respect to the shufflings of partial sequences of lengths R1 and R2, R1 plus R2 equal R. But the weak alternality means that you consider only the shuffles of sequences of length 1 and of length R minus 1. This is a weaker condition. This is not equivalent. But in the case of a doubled symmetry, you cannot weaken both sides, but you can weaken one, and you get something that is equivalent. This is, again, non-trivial, but extremely helpful. And it works for the al/al and al/il, and of course for the symmetral things. And second lemma is more technical, but it means, going from weak, the advantage of going from a weak, considering only weak alternality is that it involves only neighboring length R and R minus 1 instead of many of them, you see? So you can go from one, you see, you have forgotten, you have scratched all the degrees, but you can recover them one by one due to these lemmas. And it works remarkably well for, you see, we have we reduced everything to the extremal algebra with only unit partial weights. But in the extremal algebra, you cannot express the second symmetry because it also involves the elements of length s minus 1. But due to another lemma, actually you can write the dependency, you can eliminate. You take two bases on the, you see on the first line, you have a basis of the all alternals in the of length is and then of length s minus 1. And you write the weak alternality conditions for these two, in these two bases. And you get relation in red. And you see that there are two sets of relation. In the first set, the C's, which you want to eliminate, appear singly. So that you can very easily eliminate them. And you get a system of structure constraints. And you're automatically certain that they will define a subalgebra, precisely. So you have all the information is in the extremal algebra. You can forget about the rest. Of course, you will, if you want to be to provide a complete solution, you will have to explain how to retrieve not the lost information but the occulted information. But this is the first step in very few words. Now the second step is mould amplification. How do you go to from the extremal algebra with colors to the two satellites which have no colors? And this is again the trick of mould amplification. This is a mould operation that has three properties. It singles out a special index, omega star. Let the indices be omegas. It singles one. It adds a new indexation layer, you see the U's, and it preserves simple symmetries, alternality or symmetrality. And here we've already used that transform to define ZAG. Now we are going to use it again, but in a very different, completely different context to get to push the colors upstairs and to transform them into degrees and to construct the two satellites. So if you apply that to, there are two ways of, there are only two colors, one and one over half. So there are two satellites, there are two amplifications, and forget about the upper column, they are all zeros, and you have only the lower indices. Ones, in the first case you have strings of zeros, and in the second case strings of one. And this is what you get, and you define in this way the two satellites. And again, the first symmetry is preserved. That is simply a result of the properties of amplification. But so the things are defined. But actually, there is an important thing to understand at this point. Each satellite in itself contains the whole information. This is more or less clear from the way it is constructed. But the thing is, if you want to be to carry over the whole structure to the satellites, you need the two, because you see, if you took only one, all the information would be there, but it would be easy to handle. Actually, if you want to see how the ARI-GARI operations change form, operate them, you would have to consider in one satellite, you would have to consider small r's and large r's, pairwise. But if you consider the two, all the operations modify, and they can be defined in that. Now this is about recovering the lost information, but I will go straight to the new structure. The thing is, you have reduced everything to the extremal algebra. You have changed the extremal algebra to satellites, to pairs of satellites. And nowadays, the only thing left to do is to define, to see how the operations, ARI-GARI operations, and all the others, get modified, act on these pairs. So GARI acts nowadays on pairs. This becomes BRI, GARI becomes BGARI, and they act in a very specific way, you see. You have also to define that for the uninflected bracket LU, you see. And what you get, this is not a definition, this is not nothing arbitrary, this is what nature imposes on you. You get these operations. But there is an important caveat. It is in the absence of length one component. Actually, you see if you have colors, where if you have no color, there is no length one component in the algebra, because zeta of 1, you decree that it is 0 and you forget about it. But in the case of colors, it is not. It is convergent. It is a logarithm of 2 or minus, and you have to grapple with it. You cannot wish it away. And so in the absence of unit 1 components, the ARI structure becomes BRI, this complicated structure. You see, it acts on pairs. Instead of acting on A and B, it acts on the two satellites, and in this unexpected way. And in the case of the group, it is even more complicated, but in the case of length 1 components. And when there is when you have length 1 components, I mean, with, in this case, with a scalar in front of them that is going to be logarithm of 2, then you have additional, the adjuncts, I mean, in red, additional terms, which I cannot very define very closely, but they complicated the picture for the algebra and for the group. This becomes even slightly, and I think this is the reason why this phenomenon had not been discovered earlier than that, because you see, from the satellites, you can recover, in the algebra, you can recover, you see, the uncoloreds from just by taking the difference of the two satellites. And in the case of the group, you take a quotient of the two satellites, this quotient, and you get the original. But if you apply that to DAG in the colored case, there's this troublemaker, I mean, a logarithm of 2, length 1 component, which complicates and obscures everything. So you want to, unless you have worked in the algebra which clarifies everything, and you are confident that there exists a formula for the group. Unless you have this confidence and this background and this experience, you will miss actually the phenomenon. And so this is it. And well, the group law, the ARI-GARI, you see, this is without the complication of logarithm of 2, and with logarithm of 2, it's even more messy, but simply it restores the gradation. So, and then you can keep track of the second symmetry. It expresses itself in the satellites, not only for the difference, which is simply the uncoloreds, but for the both satellites simply. So, and there are even so many more things. So, surprisingly, I mean, given the way they were constructed, the satellites turn out to be meromorphic in hue. I say surprisingly because they are constructed from colors. You see, it's not clear how colors could produce poles, but this is the way it is. And so the first symmetry is unchanged. The second one, I mean, is modified, but not, and there is still a functional expression, not only an analytical expression, which we mentioned a moment ago, but a functional expression like alternality. And so we've been extremely lucky so far because this process worked only due to a string of improbable string of good luck. First, number one, the restriction doesn't involve any loss of information, and that information which is occulted remains retrievable algorithmically. Second, streak of luck, the satellization returned the subtractive E-epsilon structure into additive E-flexions, U-flexions, which is again mind-boggling actually. I mean, and then third point, satellization alters but does not destroy the second symmetry. It keeps everything meromorphic, again surprisingly, and it absorbs absolutely in a very natural way the Hoffman duality and the color consistency and many things. It works very nicely. So my time is almost up. And now what did we gain actually? Well, a huge, we reduced the amount of data tremendously. We restored, this was step one, and then step two, we restored the gradation, the filtration rather, by length. That is to say, at the end of the day, you can produce a formula if you're interested in a certain length. Length 3 or 4, you can produce formula that will go to infinity in terms of a degree. So the way it can go to infinity, you fix the length or depth, and you have a formula, a compact formula that gives you everything, reduction into irreducibles and everything up to infinity. This is something, I posted this in the case of Uncolored, long ago after a talk in Lille. I think, I'm not certain it was understood, but anyway, this works. And what else? So this is, no concluding remarks, yes. You see, there is life after the multizetas, because this thing of dimorphism, this phenomenon, it extends to larger Q fields, I'm certain. The ARI-GARI machinery, I think it ought to actually to do service actually also in these settings, plus possibly other things. And well, it's a beautiful structure, which even if it had no application, actually would deserve to be studied for in its own right, for its own sake. And what else? Well, the part 2 is, I mean, actually old stuff, not exactly old, but there are many articles, I mean, on my homepage and elsewhere on that. But part 3 is still, I'm confident that there's still a lot to discover. I mean, that the Flexion structure and that multizeta have not spoken their last word. But I have spoken my last word, so I'll leave you.
So I think the thing that we absolutely agree upon is that the most perplexing root of unity is the first root of unity, the uncolored case. So the Broadhurst-Kramer conjecture came from taking the obvious double thing, assuming the triple things were simple, and fixing everything at depth 4, and then the silly thing in the Broadhurst-Kramer conjecture is the full stop at the end. So how do you understand that full stop? You had a transparency where you said, and with some slight modification at depth 4, did you say?
Yes, because
if you know, no one can prove what the number of, even at the motivic level, what the number of irreducible quadruple sums is. But my feeling is that if you could do that, then you could do everything, because that's what the formula says.
Yeah, proving it is one thing, but I mean, at the intuitive levels, I mean, the number of constraints which you add by adding the colors, I mean, increases. So, I mean, to such an extent that you shouldn't be surprised actually to get rigidity by going. By the way, I found your you and your colleagues, I mean, conjecture is extremely helpful actually. I mean, and then there's since we are on the subject, I would also mean I'm limited by the computing power which we have at Orsay, and on top of that, it broke down for 1 full year. But I would like to make numerical experiments about the irreducibles also. I mean, there are many things. There are so many things to explore in this. But I think many things have not been studied for the precise reasons. I mean, I insist this algebra, although some microscopic subalgebras, I mean, of ARI-GARI can be shown to be isomorphic to Ihara algebra, etc. But the setting itself is completely different, and it accommodates poles, which are absolutely essential. Although in the end they have to disappear. They introduce themselves, and then they get rid of. But you see this creation annihilation process, which is very specific for this. You cannot do without poles in this. And the special structure, the lengths for B-symmetral, B-alternals, you see, if you look at them, at their coefficients, you will see immediately that they are more complex than the one that are produced by bracketing elementary length 1 alternals. And that additional complexity comes from the poles. They are basically strings of Newton coefficients. But I mean, if you work with the Newton coefficients, you don't understand anything. You have to work with poles. So this is, if you retain only one thing in the case of the Uncolored, I mean, retain this word poles, which exist in this framework and do not exist in the alternative or competing frameworks. So that's all I can say.
Thank you.
So if not, let's thank you again.